So now we're going to take a look at benchmarking, and we're going to compare, see what kind of performance cost there is from having to just use a composite literal for a slice where the underlying array keeps getting transferred, created, destroyed, created, transferred, destroyed, created, transferred, destroyed until enough values are there. And we'll compare that to using make, where we already have just one array, so we don't have to go through that destructive process. And we'll create a new folder, and we'll call the 013 benchmarking. And then in here, we'll create main.go, and this will be package main, and then we'll have func main, and we'll have two functions, and one function will be complit, and one function will be complit composite literal. Another one will be make way. Just be the make way. I can't use make because it's a keyword. And so for func complit composite literal, we will do for I colon equals 0, I less than 1 million, and then I plus plus, and we need a slice, so we'll do a slice, and our slice will be a slice of int, and it will be slice of int, nothing in it, right? And then we could look at the length, func.println length of II, and func.println length of our cap of II. And let's assign that to a variable. So L colon equal length of II, L, and C colon equal, ooh, that's weird, cap of II, and then, oh, wait, yeah, that all works. Why do I have I plus plus give me a deal here? Expected Boolean range expression found a simple statement. I need a semicolon. And I need to control save to bring in. And now we want to append to II. II is equal to append to I, right? And we could check our cap is C, and we'll call this temp C is colon equal to var temp C int. No, temp C is colon equal to C, and if temp C is not equal to C, not equal to length II, then C is equal to length II. And we could func.println new length, and we want cap. We could do func.println new cap. See, so we can see every time the cap is going up. Does that make sense? And we're just going to comment that out for a second. So we got our slice event in composite literal way. We created a slice of int with no values in it. So its length, what's its length going to be at the beginning? Nothing. What's its cap going to be? Don't know. Right? The runtime is going to just make one for us. We're going to print out the length. We're going to print out the cap. Now we're going to go to 1,000,000 people. And we're going to take the cap and we're going to assign it to temp C. And then we're going to append to our slice of int. We're going to append whatever our current integer is. And then if temp C is not equal to the length, temp C is not equal to the cap. Good thing I'm talking this through. So meaning the cap changed when we did our append, right? Because here we had the old value, now we have the new one. So if our cap changed, and do I need to have the temp variable? Is there some way I could do a comparison like, oh, it changed? I can't think of any way. Because I need to be able to compare previous to before, so I got the before value, and now I compare it to after. And so if it did change, I'm going to make my cap the new, I'm going to assign that to C, so that'll become the new one, right? I'm going to print out the new cap. Are you ready to run this? I'm ready to run it. I want to see what happens. So it started out, length and cap are both 0. My new cap is 1. My new cap is 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 1280. That's different. It didn't follow the doubling, right? 1696 is starting to pair off, you know? So it's not just creating this massive allocation of memory that's now available to store data in it. Like it'll give me up to whatever 1024 is. If it's a slice, well, I'm thinking of the underlying array as the capacity. So I don't know. But anyhow, right? And for 1,000,000, it takes me up to 1,136,640 is my cap. That's kind of cool, right? You can see that cap being created. But if we do the make way, we're going to say that II colon equal make slice of int length 0 cap we're making that underline array one time, okay? And then we're going to do this. Put all that same code down here, so it's got to grind through the same stuff. And we'll do all the same checking, even though we know it's not going to change. And we'll put this in make way, right? So we could see if make way prints out. And maybe we'll just add that to this up here. So we see we switched over. I can't put that there. And we don't really need to see the values that are being appended. So let's just see those run. Right, there was our initial length and there was our cap. Now let's benchmark them. So for benchmarking, we go back to the testing. So we go golang.org, packages. Testing. And it's testing, then we have benchmarking. And so to do benchmark, you got to have functions benchmark testing B. And so we're going to need to create a new file. And this is going to be main_test.go. And then this is going to be package main and func main. And then we're going to have, sorry, not func main. We got to have benchmark XXX. This is adult only, folks. Benchmark, and we're going to benchmark, what was it? Complet. And it needs to have B, which is a pointer to testing.b. So B is a pointer to testing.b, and then we want right? We want all this. But instead of this, we're going to call comp lit. And so what this says is that, you know, for some number of times, it's going to call this, and it's going to run it like maybe 100,000 times, and then get a time. How long did it take me to do it, each of those on average 100,000 times? So that's, I think that's it for benchmark. Nanoseconds in operation, right? So let's benchmark comp lit, and now let's benchmark, what's the other one we wanted? What was it? Make. Was it just make way? It has to be make way. Make way. And we're going to call make way. And I think that's it. So now we do go run test. And I think we have to add a flag. Command when its bench flag is provided, okay? So go test command when its bench flag is provided. So I'm going to do go test dash bench. I think I need to add the file. Do I? I just run it. Missing argument for flag bench. Run go help test or go help test flag for more information. Missing argument. So go help test. And star._test.go. Let me just look at my examples here. Like I said, it's been a year. I have no idea what section that is, section 07. Not my favorite repo. Here's my code, man, 6, 5. Code samples. That's better. Testing. Benchmark. Remember to bet. Benchmark, example, test. Benchmark, example, test. Go doc, go test, dash bench. Maybe I need the dot. So the make way cap was what was that? 2.2 million nanoseconds per operation. Oh, it's printing all that stuff out. I don't want to see all that stuff. Let's get rid of that. It's like way too much to dig through all these prints. L's declared and not used. Length I. I'll get rid of it. Declared not used up here too. Okay. So using composite literal, it took us 5.9 million nanoseconds per operation. It ran this test 300 times to come up. We ran through the code 300 times to come up with that average or whatever. And using make, it took 1.1 million nanoseconds per operation. So that's like a 20%, you know, that's like 5 times faster. That's 5 times faster using make versus complit. Now, why does this matter? Dude, nanosecond, who cares, right? Like 5 million nanoseconds versus 1 million nanoseconds, who cares? But when you build Facebook or GitHub or Twitter and you need to push out, you know, trillions of messages a day, and you know there's like 700 million people who tweet, and each time they tweet, their tweets have to go to somewhere between, you know, 20 to 26, 50, 65 million people. Like, that's a tremendous amount of processing. And when you start to process at that scale, like, you get really concerned about whether or not something takes 5.9, you know, nanoseconds or 5.9 million nanoseconds or 1.1 million nanoseconds. And you're like, we're using make all the way. You know, like whatever situation that would be in. Isn't that interesting though? So when people who created Go, they wanted performance. They wanted, you know, efficient execution, efficient compilation, and ease of programming. So when you write your tests, you could also write these benchmarks so that when you run Go test against your code base, everything's passing, and here are all the speeds at which stuff is running. You know, I mean, eventually a large team, you can leverage this into people who are optimizing for performance. You could have A/B testing where something new gets deployed, and you know it's all going to work, but which version's faster, the new version or the old version? So you can compare those. It's mind-boggling. It's totally overwhelming to try to think about doing something like this on your own. I know somebody who's like high level, coded C for 20 years, C++, and took on Go. It took him 6 months to understand the language specification. And then somebody else who's super high level, the guy's, he said to me, I bought all these domains. I never end up doing anything with them. It's like he has all these visions about what he'd like to build, but it's so overwhelming, one person. But this is what's possible. So this is what YouTube is written in, is Go. It's all written in Go. Google's being rewritten in Go. It's the future. How many people liked seeing that? Only 20% of the class. Other people are like, it was too much or it's too late. All right. Oh, that was cool.